in physics, and I had a dissertation there, which was based on organic electronics and semiconductors. Um, After my master's, I wasn't too sure if I wanted to do a PhD or if I just wanted to get a job. So I think I was more keen on getting a job and earning some money. And I just applied for a PhD to one university, that is Cambridge University, thinking that there is no way that I will ever get accepted to Cambridge. That imposter syndrome that you don't get into Cambridge just like that. So it was just like, let me just apply to this place. Most likely I won't get it, and then I'll go and apply for jobs. But I'll have this feeling like I tried and I didn't get a PhD offer. Believe it or not, I got a PhD offer from Cambridge. I got a place to study at Cavendish Laboratory. I still didn't want to take that place. I was like, no, I don't think I want to do a PhD. And my dad was really like, you would be really stupid if you reject an offer from Cambridge. So I think you should go. So I went. I didn't have funding back then, and my dad was happy to sponsor my PhD for me. And that was even more like, there's no way I'm going to let you pay for my 5 years of my PhD. It's very expensive in England and this and that. The funding situation is not the same in UK as it is in US. So, but I still went, and believe it or not, when I went there, my supervisor was able to offer me a really good scholarship. So he put me on a project which had really good scholarship. So I got a lot of the funding from there. And I was just really happy, like I made the right decision. I came to Cambridge, and I even got a scholarship, and my dad supported me a little bit. But it just felt like, okay, I was made for this. I just applied to one place and got an offer, and now I have funding. So yes, this is for me, and I'm going to do it. So I spent a little over 5 years at Cambridge, a total of about 6.5 years in the UK. And then after my PhD, it was quite a stressful experience overall, as all of you might know who are doing PhDs. Um, I had a little break after my PhD, and then I started applying for jobs. And I got this postdoc fellowship offer from UT Austin with Professor Akinwande. And I took that offer. I moved to the US. And finally, I am about to finish my postdoc as well in the next couple of weeks, in the next week actually. And then I'm moving to the next phase of my life. I always wanted to do a job even after my master's. And I'm finally going to do a job like in the corporate world. So I have a job offer from Intel. I'm going to be working as a process integration engineer at Intel in Hillsboro in Oregon. And I'm moving there next week. And really excited for this new change. I feel like I've seen academia so much over the last few years. I've only been doing academia so far. So it really is a time for a big change for me. And I think that is why it's a good way for me to wrap up things and say goodbye to UT by talking about my experiences. Um, so I'm going to talk now about my research. I'll give you an overview of my PhD research. I worked on a compound semiconductor system called gallium arsenide, aluminum gallium arsenide. And these wafers are grown using a technique called MBE, or molecular beam epitaxy. It's a technique to grow very high quality semiconductor 3.5s. You can vary the semiconductor composition with a really good precision using this method. So I was given these wafers by MBE growers, and then I would take them to the clean room. These wafers, I would take them to the clean room, and I would work. This is what a yellow room in the clean room looks like. When you do photolithography, you have to work in a yellow room like this. And you would take these wafers and you would fabricate them into a tiny little nanoscale device. So I would take these, go to the clean room, do a lot of processing, and fabricate some novel transistors on these wafers. And because my PhD was in semiconductor physics, we were interested in looking at the basic fundamental physics of the charge carriers in these devices. So I had to take these devices and cool them down to really low temperatures, temperatures as low as 70 millikelvin in what is called a cryostat. So this is a picture of a cryostat laboratory. That's me just dealing with a nitrogen filling dewar. The dewar is filled with nitrogen, and you have to fill these cryostats with liquid nitrogen and helium pretty much on an everyday basis. So every time you are doing measurements on the cryostat, you don't have a holiday. There's no weekend. There's no Christmas. So I remember going in every single day because my cryostat needed a fill done, and it would just warm up if I didn't do a fill. So especially towards the end of my PhD, I was spending every day in lab just doing these nitrogen and helium fills and measuring my devices. So it was I had to work really hard. Those 5 years were a lot of hard work, I think. But in the end, when you earn your degree, I think that's a very good investment. So I want to give a little background on what are these materials that I worked with. I worked with these gas algas, as we call them, gallium arsenide, aluminum gallium arsenide heterostructures, and these are essentially low-dimensional semiconductors, which means that the charge carriers in them are restricted to move in one dimension or the other. So typically, the kind of system that you come across in your everyday life is a three-dimensional system, right? Where you have electrons moving in all the three dimensions. You have freedom of motion in all the three dimensions. But it is possible to restrict the motion, let's say in the z direction, and then the electron only moves in the xy plane. And what results in this case is called a 2D system or a quantum plane. You can even restrict the motion further, and what results then is a 1D system, and this is called a quantum wire. It's a 1D quantum wire where the electrons only move in one dimension. And then finally, when you restrict the motion in all the three dimensions, what results is a 0D system or a quantum dot. It's essentially like a puddle of electrons which are not free to move in any direction. They're just over there in a puddle. So when the importance of this is that when you restrict the motion of the charge carriers in one dimension or the other, then the dimension in which you have constricted the motion, the energies in that dimension start to become quantized. You start to see quantum effects in the dimension that you have restricted. And my PhD was focused on looking at these quantum effects. So you had to cool down the devices to remove all sorts of like heat effects and heat energies and those kind of things, and just basically look at these quantum effects where the energies are on the scale of millikelvin. So you have to really reduce all sources of heat and cool down the devices to look at the fundamental behavior of electrons. So that was what my PhD project was. I specifically worked with 1D wires, 1D quantum wires. I'm just talking about one of the projects. I had a couple of focus projects. One of the main projects was to look at Coulomb drag in coupled 1D bilayers. So what exactly is Coulomb drag? If you consider two bilayers, two layers in close proximity with each other, then because the separation between the two layers is very small, of the order of nanometers, then when you pass a current in one of the layers, because of the proximity of the two layers, there's momentum transfer from one layer to the other, and you start to affect charge transport in the second layer. And this is called Coulomb drag, where carriers in the second layer get dragged because of current passed in the first layer. Um, and this gives you an idea of the kind of interactions between the charge carriers in the two layers. So this was one of the major motivations of my project. I wanted to come up with a design where I can study Coulomb drag into 1D quantum wires. There's a lot of studies on Coulomb drag between 2D layers or bilayers, but there's not a lot of studies on Coulomb drag between 1D wires. So you might ask, like, what is the importance of this? And so even though my project was more fundamental in nature, we were trying to look at the physics of these systems. I believe that in the future it would become as the transistors and all the small little transistors that go in an integrated circuit are shrinking in size. it would become really important to understand the behavior of electrons in such devices which are so close together, where the circuits are so close together that the transport in one circuit starts to affect the transport in another. So I feel like whatever we learn from these kind of fundamental studies could be very useful in the future, where drag phenomena can start to affect transistor performance. So I get that question a lot, like what is the importance of this? So I believe we do research from a fundamental perspective, but your results and your findings will definitely be of use in practice sometime in the future. So it's not a waste of your efforts. It's you're doing new things which will be useful in the future for sure. And because my PhD was in physics, we had to do these kind of fundamental studies. We were not focused on applications so much, but we wanted to look at the fundamental behavior of electrons at low temperatures. So this project was very intense in terms of sorry, in terms of the device design. I had to come up with a device design to couple two 1D wires in close proximity with each other. So I first worked to develop these 1D wires. This on the left hand side, you see an SEM image of a 1D wire. You have constricted motion in this dimension. It's only 167 nanometers in width, and you have free transport in this direction. So this is why this is called a 1D wire, because you only have freedom of motion in this one direction. So I first had to come up with a design, and then I used etching to define my 1D wire. I did a lot of imaging. I tried so many different etchants to try and find out which etchant works the best. And then the device design for fabricating these coupled wires was really complex. The wires had to be defined in a gas-all-gas heterostructure system. So there were several layers of processing. There were 4 layers of processing on the top side, and then 4 layers of processing on the back side of the device. And it was just a really complex, fabrication intense project. And it would take me about a month and a half in the clean room to finish fabricating one batch of devices. And for those of you who work in the clean room, you can imagine how difficult that is. If you make one mistake in any of the steps, then you really have to go back and start from step one. So yeah, this was really very nerve-wracking. There were times when I struggled so much, I would make a mistake and then go back, and it just used to feel like a lot of disappointment when things did not work. But eventually, as with anything in life, if you keep with something, if you keep putting your efforts, at some point it will start to work. And so, sorry, I'm going to come back to that. And so, when I started measuring my devices, I was able to see signs of 1D conductance quantization, which is a quantum effect that the conductance of a 1D structure is quantized in units of 2e squared over h when you measure at low temperatures. So this just shows that as you reduce the temperature, you start to see these 1D plateaus. And so eventually, all my hard work paid off, and whatever I was trying to accomplish, I did achieve. It took a lot of time, a lot of trial and error, but finally I was able to make the devices that I wanted to make. Yeah, so with the previous slide, I just wanted to show how fragile these devices were. So once you do the front side processing, you would have to put the device face down on a host substrate and then fabricate the backside. And these devices were really thin. They were less than 2 microns thick. So you can imagine how difficult it would be to handle them. Although they are mounted on this host chip, they were still very difficult to handle. So yeah, it just shows the kind of complexity that went in fabricating these devices. So I wrote about my struggles. I was struggling for the first 3 years. I didn't have a lot of results to talk about. There was a lot of training involved, and I didn't have a lot of results for the first 2 years for sure. Towards the end of the second year, I started to get some results, and I wrote about my struggles in our college magazine. If you're interested, you can ask me for it. I can send you this. it's a very emotional write. I wrote about how I struggled, and how finally I had my eureka moment when my devices started to conduct and those kind of things. So it was a very emotional journey. Having said that, I feel like uh, there were many great aspects to my PhD. It was a culturally enriching experience. I was at Cambridge, one of the world's oldest universities. It's more than 800 years old, and you interact with a lot of bright minds. We had these formal halls. If you've seen Harry Potter movies, you would know what I'm talking about. You would sit down in long halls and you would get served a three-course meal and interact with people sitting next to you that you don't know from before. So those kind of things. So it was a really stimulating experience. I made lots of really good friends. Had some really stimulating conversations with lots of different people. So that was one of the best parts. I also got to travel for free to present my research. I went to Japan and I went to a place in the UK called Sheffield. I presented my research. So that was another good part. I also spent a lot of time teaching and mentoring students. So I did some undergraduate demonstrations and practical labs for undergraduates. I also did some private tutoring for school students. So this was a good way of increasing your teaching capabilities and also earning some money at the same time. So of course there was a lot of hard work, but there were some really good aspects to the PhD as well. I really want to stress this part. If you're doing a PhD, then I'm sure you're struggling. There is no doubt about it. You have to do a lot of hard work and you struggle at times. But I think most importantly, it really seasons you as a person, as my PhD advisor used to say. You gain a lot of strength, both mental and emotional, and it just prepares you for the next steps of your life. And that's exactly what it did for me. And I'm looking back, I think I'm really very happy that my dad forced me to go to Cambridge, and I can't be happier about that decision. Um, so I graduated in a very traditional ceremony, and the whole ceremony was conducted in Latin because it's such an old school. They have a very traditional way of graduation ceremonies. In this picture, you see that I'm bowing down, and the vice chancellor of the university is holding my hands. And this is a tradition that they follow. And then the vice chancellor says something in Latin, which means that he's granting me the degree, and then I'm a doctor. I'm a PhD after that. So I think just going through this one day of ceremony made me feel like all of my tears, all of my hard work was really worth it because it was such a special day, and I feel like it was the right decision for me. So now I want to talk about my postdoctoral life in the US in Austin. So I moved from after having spent almost 7 years in England, I moved to the US, and it took some time getting used to things. I was not used to this kind of a weather. People say that we have this kind of a weather in India, but I had been away from India for such a long time and I don't do good with heat. So I did not like the weather here. It took a lot of time to get acclimated to Texas and the heat. And then how do you really travel around? I used to Cambridge is such a small town that you can just cycle everywhere. You can cover the whole town by cycling. And then here, how do you commute to lab? Well, you need a car. So I realized pretty early on that you don't have a life here if you don't have a car. So that was another big change. I didn't really drive much. But being in Texas, I had to buy a car to get around. So that was another big change. And then just generally, like the way people speak, the kind of colloquial terms that they use are very different here and in the UK. And although like these are small, trivial things, they do matter a lot when you're getting settled down in a new place. And the sooner you realize about these differences, the easier it gets for you to call that place your home. So I believe it took me quite some time to make that transition from UK to US, and getting adjusted to the several things, several changes that there were. And in terms of research as well, I think most people prefer to do a research, their postdoctoral research is usually along the same lines as their PhD research. But for me, that was not so much the case. I worked on semiconductor 3.5s, gas heterostructures. Um, these are really high mobility, very precious wafers. Whereas here I work on 2D materials where you basically take a tape and exfoliate the material. So it's up, you can make as much as you want. And the ways of working in the clean room are also very different. In my PhD, I had to be really careful to not waste anything, like no wafer, nothing, because they were really expensive. So I had to be really meticulous in the way I used a wafer. But here, when you're working with 2D flakes, if something doesn't work, if you don't get a flake that you want, you can just discard that batch of exfoliation and those kind of things. So it took me some time adjusting to the new field of research. It took some training. It took a lot of reading and those kind of things because I made this switch from 3.5 to 2D materials. It was a big switch, I feel. So I'm going to talk about my postdoctoral research a little bit now. I'll just introduce the materials that I work with. I work with these materials called exenes, these 2D materials called exenes. They're basically mono-elemental 2D materials made from group 14 of the periodic table. For example, a 2D sheet of silicon is called silicene, and it's an exene. A 2D sheet of germanium is germanene, and that's also an exene. But now that more and more materials are being discovered, this definition of exene is being expanded to include elements from group 13 all the way to group 16 of the periodic table. So even a 2D sheet of selenium called selenine is an exene. So this is one class of the materials that I work with. The other class is called the TMDs, or the transition metal dichalcogenides. So they're essentially materials of the form MX2, where M is a transition metal, which is sandwiched between two atoms of a chalcogen. So you take sulfur, selenium, or tellurium, and you sandwich a transition metal atom in between two atoms of any of these materials, of these elements, then you get a TMD. This is how a cross-sectional view of the TMDs look like. So this was another class of materials that I worked with, the exenes and the TMDs. So these were the two 2D materials that I worked with. And as opposed to my PhD, where I had a couple of really focused projects, you just worked on two projects for 5 years. In my postdoc, I had to multitask. I had several different projects at the same time. I guess that is a basic difference between a PhD and a postdoc. You end up having a lot of responsibilities as a postdoc. You have to mentor students, you have to do admin things, you have to teach, you have to deal with a lot of projects at the same time. So again, that took some adjustment. So I worked on one project where I had to do the development of transistors based on exenes and primarily silicene. I was involved in the development of a transfer setup, which would help to pick and place 2D materials. And we had to install this in a glove box because we wanted to be able to work with unstable materials. So I led this project of building a transfer setup. This was a really big project. I worked on it for almost 2 years. And then several other projects, some growth projects, and several other miscellaneous projects, some industry projects also. And I worked with a whole bunch of different students for all of these things. So let me just, I won't go into too many details about the technicalities, but for my exenes project, we were interested in developing a transistor on silicene. This had been demonstrated for the first time in our group led by Professor Akinwande and this postdoc, Li Tao, who was the postdoc before me on this project. So they worked together and demonstrated the first silicene transistor ever. And why this is such a big deal, it's because silicene is very unstable in air. It oxidizes fairly rapidly within a couple of minutes. So being able to fabricate and demonstrate transistor action on a silicene transistor was a big deal. And if you go and look at this paper, this is one of the highly cited paper of all times, of this age. So the way this works is that we have some collaborators in Italy, and they ship us these samples where we have a block of mica on which we have a thin film of gold, and then they deposit silicene on this gold using MBE. And because it's so reactive, it has to be capped almost immediately with aluminum oxide. So this is how a stack would look like when they would ship it to us. We have mica, silver, silicene, and aluminum. And then we would fabricate that into a device using this method called SEDNE method, which was developed in our lab. It's the silicene encapsulated delamination with native electrodes. So you would have to detach it at this interface and get rid of mica, and then flip chip it on a host substrate, like a silicon oxide host substrate, which would act as the gate. And then the silver electrode has to be patterned to form the source and the drain contacts. So this was a method that Li Tao had demonstrated and got a lot of recognition for developing this technique and demonstrating the first transistors. But this technique had some the yield with this technique was not too high. So obviously this was the first ever transistor, and so that was a big deal, but there were still many things that required optimization. So when I took over, the first generation of transistors was demonstrated, but we had to work on improvising the yield of the devices. So um, we worked on improvising the yield by growing some extra alumina and metal on the device stack once we received it, and then we put it face down on a host substrate, and then we got rid of the mica and stuff, and then we patterned this. We got rid of it once we had it on the host substrate, and then we patterned the source and the drain contact. So just this additional deposition of alumina and metal gave more strength to our entire stack, because if you get rid of this mica, then essentially you're dealing with maybe less than a micron thickness of a stack, but having this additional metal and alumina gave the stack more strength, and we realized that this technique could improve the yield of the devices. So we published the idea of this technique in our paper, this one, and we are now about to publish another paper where we have demonstrated we have demonstrated this fabrication technique in practice. And I have worked with two really hardworking graduate students on this project. That's Hasib, who's at UT, and that is Gabrielle, who's our visiting scholar from Italy. So all three of us worked really hard on this project, and we were able to demonstrate this process in action. And finally, we're publishing something on this. Then the other project that I talked about is I led this big project of developing a transfer station, which would help us to pick and place the 2D materials and make designer heterostructures. These are called van der Waals heterostructures, where basically you can pick and place any 2D material at will and stack them in any fashion. So this is really like materials by design kind of a concept, where you can think of Legos, where you can just pick and place any Lego and make whatever you want. So it really is a very upcoming field of research where you can put materials at will, and these can even be rotated with respect to each other, which is another really hot topic these days. So the way this works is that you start with a glass slide which has a stamp attached to it. The stamp is usually made up of a polymer called PDMS, and you stick this polymer onto the 2D material that you want to pick up. And using a combination of pressure and heat, you can pick up the 2D material and then drop it on another desired location, maybe on top of contacts or any other 2D material at a slightly higher temperature. So this technique exists, that you can pick up and place the materials using a PDMS stamp. People have been doing this in our lab at UT as well, but we wanted to be able to work with some additional materials which oxidize very rapidly in air. And so we wanted to have this transfer set up inside a glove box. And you can imagine if this kind of a setup is in a glove box, we want to automate most of the motions, this movement of the glass slide, of the substrate, and these kind of things, because you really don't want to have your hands inside the gloves all the time and maneuver all the stages. So I took up this project and I led this project with a team of technicians and graduate students. And we made this setup. It is a very state of the art automated transfer setup. It comprises of some really specialized parts, which are very expensive, and three different PIs collaborated on this project, pitched in a lot of money. So we have long distance objectives, we have this glass slide stage, and the motion of this is completely is automated in Z. The motion of these objectives is automated. Then we have the stage, the sample stage, which can be moved in X, Y, and even rotated. So this rotation stage was one of the most expensive stages that there are out there, because you can move with a very you can have an incremental motion of a very small degree with this stage. So that is why it's very expensive. Um, so it took a lot of time procuring all of these parts, designing this with the help of graduate student, and putting everything together. And it took me almost 2 years to bring this all together. I'm just showing you a picture of before and after, where we had this glove box in one of our other labs, and it was basically empty, nothing was in there. And then after a lot of hard work, we were able to bring it to this stage where we have a completely motorized transfer setup in the glove box. Its usage is restricted to very few students and postdocs, because it's such a state of the art equipment. As you can see, it took a lot of time, effort, money, collaboration, manpower, and a lot of resources. And I'm happy that I was able to accomplish all of this during my time at UT. Um, with this, now that we have this, it is possible to do a lot of exciting things, such as this field of twistronics, which I mentioned before, which deals with how the twist or the angle between 2D materials changes their properties. So when you put 2D materials on top of each other at a slight twist, then the properties of that stack of that van der Waals heterostructures is very different from the properties of individual 2D flakes. And very recently, superconductivity was demonstrated for a bilayer graphene heterostructure, where the two layers were twisted at an angle of specifically at an angle of 1.1 degrees. And this is actually also called the magic angle, where there's a set of these magic angles predicted by a renowned physicist at UT, Professor Alan MacDonald. So he's predicted the existence of a set of these magic angles, and at these angles specifically, the bands of graphene, they start to become flat. You start to get flat bands, and because of that, a lot of interesting properties start to emerge. And as I said, superconductivity has been demonstrated for these bilayer graphene twisted at an angle of 1.1 degrees. And there's a lot of interest in this field right now, in the field of twistronics. And we think that it is possible that this could, just bring about a new era of technology with some far-reaching consequences in quantum computation and even electrical transmission. So I feel proud that I was a part of a project that could, in the future, enable such technologies which could have far-reaching effects. So now I just want to quickly wrap up my postdoctoral experience. I think it helped a lot in broadening my horizons. Because I was able to work on so many different projects, and also because I made this transition from 3.5s to 2D materials. I feel like I learned a lot about so many different semiconductor materials. It definitely was a big challenge transitioning, but I think in the process I ended up learning so much more than if I had continued with with my PhD project. So I think again it was a really good decision for me for to take up a postdoc position in a slightly different field. It definitely helped in expanding my knowledge. It felt really different and special being on the other side, where as a PhD student, you're submitting your manuscripts and you get a lot of comments from reviewers. When they send you bad reviews or like critical comments, then it's not such a happy feeling. But just being on the other side, where you are reviewing other people's works, it gives you a sense of responsibility, and you do feel special as well that now you're on the other side and you've earned this right to kind of judge other people's science, other people's research. So I think that was another major positive um, experience through my postdoc. And then finally, I think I was very fortunate to have worked with so many different students on so many different levels, like high school students, undergraduate students, graduate students, some postdocs in our lab. So it just felt like a very enriching experience where I got to work with so many bright minds, so many young students with lots of energy. So yeah, I think that was one of the major highlights of my postdoc experience here. Um, Talking about the next thing in my life, as I mentioned before, I am switching from academia to industry. I had always wanted to work in the industry and see research being transformed or translated into something more tangible, where you can come up with a product that people can use and it can better their lives. So I think working at Intel as a process integration engineer, I'm going to take a lot of my clean room skills with me, a lot of the things that I've learned through my training at Cambridge and at UT, and all the skills that I have as a clean room expert, and be able to use that in defining and working towards the next set of technology in the industry. I think I'm really very grateful to have got this job, and I'm really looking forward to this next phase in Hillsboro in Oregon. I'm moving next week. So, just before I end, I want to share some of my learnings, some of the pieces of wisdom that I've gained over the years. If you're doing a PhD or a postdoc, I think it is not something that is very easy to do. It takes a lot of strength and effort. Um, it is a test of your perseverance. If you are facing struggles, it's just a part of it. You have to keep bashing every single day. My PhD advisor used to say this when I was the writing of my PhD thesis was very stressful as well, and he used to tell me to just write a little bit every day. Writing is not easy. Just write a little bit every day. Just keep bashing every single day, and one day you'll realize that you have a thesis in front of you. So I want to say, if you're struggling in any aspect of your PhD, be it experiments or the writing, or even coming up with an idea to do research on, just keep at it, and one day you will definitely get there. Um, it definitely seasons you as a person. As I said before, you develop a particular personality. You learn to deal with failures, with struggle. It can get very isolating at times because you're with yourself all the time. You're working on your projects by yourself. So if you're feeling isolated, do not suffer in silence. I would suggest to reach out to your fellow friends, maybe take some counseling or therapy if required. Um, Talk to your advisor and those kind of things. Just do not suffer in silence, because this is very natural. It's very natural to feel isolated in a PhD. Uh, Definitely develop something outside of your lab. I remember I used to do a lot of yoga and these kind of things to keep my sense of calm. If you have a hobby outside of lab, then that definitely helps. You might think of it as time away from lab and not something that is worth it. But once you develop a hobby and you keep at it, then your productivity in your research will also increase. I know that for a fact. And in the end, once you've graduated, once you have your next step, maybe a postdoc or a job in the industry, I think it'll all feel like it's worth it in the end. Um, I just want to end with one of my favorite quotes. And I look back at this anytime I'm struggling. I think to myself that I should take pride in how far I have come and definitely have faith in how far I can go. So, yeah, thank you for listening to me. I will be very happy to take any questions that you have. And even after I leave UT, I would like to stay in touch with all of you. And please feel free to reach out to me on any of these emails. I don't know how long this UTexas probably stays for you for life, but I don't know for sure. But feel free to email me on any of these emails. And if you have any questions right now, I can talk about them also. Rachel, do you want to take over?
I think Dimitri had a question. Uh, is 2D form of carbon carbonene? I don't
Oh,
know if
no, the 2D form of carbon is graphene. We don't call it carbonene, and it's actually not considered an exene. It's just graphene on its own. And I think it was the first 2D material that people started working on. Uh, yeah.
any other questions from our participants. Yeah. Thank you so much. Uh,
What is your best advice for a graduate? Martha has asked this question. What would be my best advice? Um, my best advice would be to not lose heart. I know that it is very easy to start feeling down when things are not working, as is the case with research. It's very easy to feel down, and especially when you've given it so many trials, and if it still doesn't work, you start to feel down. It's natural to feel that way. But I think my best piece of advice would be to not give up. That this is something that I've learned through life, not just through my experience as a PhD and a postdoc, just through life. I want to talk about Intel and how Intel was really my dream job. I remember when I was young and I was in India, we used to get advertisements of Intel on television, right? And Intel has this tune of ding, 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 and somehow that tune just appealed to me so much, and I kind of that became my dream job right from those times. And I feel I wanted to get a job at Intel after my masters. Then even after my PhD, I did try making some job applications, but the entire industry is in the US and nobody would hire me from the UK for a job at Intel in the US. So it felt like the right choice to do a postdoc and use that as your stepping stone for a job in the industry. I never thought of myself as a professor. I know that I wanted to enter the industry. So this is my piece of advice. If you really want something, just keep at it. Don't give up. I know there will be times when you would want to give up, you feel like it's not working out, it's best to give up, but don't give up. And even if something doesn't work in your favor, that should not mean failure to you. If one door closes, then I do believe that God or whoever you believe in, the superpower, opens another door, which is even better for you. This job at Intel that I'm getting right now, I would never have got this job without a PhD. They only hire PhDs for jobs like these. So I didn't want to do a PhD, but I wanted this job. So there's no way this could have happened. And I think doing a PhD and getting that Cambridge experience just feels like everything happened for a reason. And I'm just very proud looking back. And I think that is my best piece of advice for a graduate student. Do not give up. No matter what you're struggling through, do not give up. I also got a question where someone is asking, how do you establish a good relationship with your PI? So different PIs have different ways of working. my PhD advisor is very different from my postdoctoral advisor, Professor Akinwande, and it felt like a big change to me. My PhD advisor was also the head of the group. He was a really senior member with, a lot of admin responsibilities. So I didn't get a chance to meet with him on an everyday basis, or even, I think I met him over the 5 years I did my PhD. I met him maybe 10 times, like one on one for research works. Um, and here we have meetings twice a week with Professor Akinwande. So you will have different working styles with different advisors. But I think a good rule of thumb for having a good relationship with your PI would be to set your motives right. Like, just if you know that this is the area you want to pursue, this is the research that you want to do, then establish that with your PI. Make sure you're both on the same page, and he or she agrees that it's good for you to do this research. It's good to be on the same page at all times. It's good to be more open and clear about what your intentions are for the next year or the next semester and those kind of things, and make sure you both agree with each other. I think that would be my one tip for keeping and maintaining a good relationship with your PI. Any other?
Thank you so much, Diganti. The talk was very inspiring. And as a PhD student myself, I could relate to a lot of things that you said, and I will definitely take home what all that you said. And I'm really interested in reading the sad story that you wrote
Sure.
in
Yeah,
your Cambridge
I
magazine.
think it's not really that sad. It's more kind of inspiring. I talk about my struggles, and then that really happened with me, like my eureka moment when I had tears in my eyes because I really had been struggling so much to get my devices to work. And the day that they worked, that was really my eureka moment. So yes, I can. After this talk, I can email you all of you my.
Yeah, I'm sure that'll inspire a lot of us going through, like PhD journey ourselves. So
Sure, sure, yes.
thank you so much.
You're
Thank you.
welcome.
And for all the participants, if you can take a minute to take this poll, it's just like a couple of questions. We just want to know if you are IEEE member and what do you think about today's talk so that we can plan more in the future. So that's it about that. And so we are the IEEE graduate student chapter here at UT. Please reach out to us. This is our email, ctsstemsgrads@ieee.org, and this is our QR code. We are on Facebook, and you can also find our website here. Yeah, please stay connected with us. If you are a postdoc and you would like to share your story, just like how Deepanti did, please reach out to us. We would like to host you for an event, and stay connected with us, and stay safe during this time, and stay connected with people virtually. Thank you so much.
Thank you.
Thank you.
This poll has ended.
Yes.